Hi, welcome along to a little video on line spectra. You need to have just watched the video on YouTube of the guy putting the diffraction gratings in front of different gases, and then we're going to try and pick up from there. So let's have a look at what you were explaining, what you were seeing. And I guess there are kind of three elements that need explaining. The guy had a tube of gas. You couldn't see that very clearly, but it would have been connected to a high voltage. He had a thing called a diffraction grating. Now in the first videos, when we looked at the wave and photon model of light, you saw some white light passing, or a picture of white light passing through a prism and producing a kind of spectrum or loads of different colours. The diffraction grating does the same thing, it just does it better. It's a better way of splitting light up into its component colours. And what we then saw was that the spectrum, rather than being a continuous spectrum like it was with the incandescent bulb or the ordinary bulb, which produces all colours, we saw a line spectra which might be represented kind of something like this. So you might see a blue line, we might see a couple of green lines, or we might see a red line, and that's what's referring to as a line spectra. And each one of those lines is a specific wavelength or a specific energy of photon. We're going to go back to this little tube here and see if I can explain why that's emitting light. How this splits this up into different wavelengths will be done much later in the course. It's fairly technical. And then we're going to think about why we've got this this picture here of the specific allowed wavelengths, and we'll pick up the maths of what's going on in a later video. So we're going to expand that tube. So let's imagine this is glass, and inside maybe we've got a gas like neon, which has a very distinctive spectrum, and we've got a couple of metal electrodes, and we've got a really high voltage. So what happens is there are atoms floating around, and an electron, we can imagine this being positive end, this is negative end, goes shooting off down the tube. It's excited, sorry, not excited, it's given energy, given kinetic energy by that voltage, by the fact there's positive charge in front and negative charge behind, and it interacts with an atom. And I suppose we should be clear there are three possible options. The one is the kind of null option, the nothing happens option. The electron interacts with the atom and no energy is transferred, and it just carries on its way. The two interactions we're interested in is it gives some energy to an atom, but the atom remains as an atom, and the electrons all remain in the atom, but some energy is absorbed. And then I guess the other term we need to tackle is ionization. So it's possible that this electron comes along, hits this electron inside the atom, gives it so much energy that that electron is removed from the atom, leaving a positive ion, and that's called ionization. So that's one of the outcomes. I'm not going to spend very much time on that for the moment, but I wanted to include it as a possibility. What's happening most of the time is that this electron absorbs some energy from the kinetic energy of this electron, and that causes an event called an excitation. So how do we represent an excitation? Well, I'll start off with the diagram we don't use very often, but I think it's an important one. We've got the electron kind of around the atom. We're trying not to avoid that orbiting model, but it's got some energy in it. It's a certain mean or average distance from the nucleus or the rest of the atom. It gains some energy, and that means on average it's got more energy. We can't say definitely where it is, but on average it's further out, and it's got more energy. But I don't find that particularly convenient. And it turns out that there are only certain allowed or quantized states of energy, and that's why this area is called quantum physics. There are only certain allowed energy, so we're going to represent those as like ladders. Now they don't physically exist. Each one of these energy levels refers to a slightly different distance of the electron from the nucleus. And the lowest one is called the ground state, and that's ordinarily where all our electrons are in an atom. So draw an electron here. An electron comes along, that's the electron accelerated back down the tube. Let's move it up a bit so you can see that. Collides, passing on some energy to this electron, and that's what's causing the excitation. There are other means of excitation, but for the moment we're talking about excitation by another electron. So this electron now exists in this higher energy level. It's further away on average from the nucleus, but that's not a stable arrangement. So it has to lose energy and return to this ground state. And it can do so, it does so jumping between energy levels. And as it jumps down, it has to give out energy. And it gives that energy out in the form of a photon. And because these are discrete or quantized fixed energy levels, the energies of the photons given out as the electrons move between the energy levels is also fixed. So if we jump a long way like this, that might give rise to a blue photon, because a blue photon has a lot of energy. If we jump down a small amount, then we might release a red photon, because that has a smaller amount of energy. So if we go back up here, each line corresponds to a different energy of photon, and each line represents an electron moving between two different allowed energy levels inside the atom. Because each element, each type of atom has a different set of energy levels, each element has its own unique fingerprint or signature of a line spectra. So we can use a line spectra to identify an unknown element, and that can be particularly important in astrophysics where we can't use other means. So we're going to stop there, and we'll look at the maths in a further one. Key ideas: excitation is caused by a collision between a fast moving electron and an electron atom. Could cause an ionization if it's got enough energy. But what we're into in this topic is the excitation of an electron to a higher energy level, followed by the de-excitation. It's not a term I particularly like, but it's the one we use, into a lower energy level, losing the energy in the form of a photon, and the colour of the photon, just like before, corresponds to the amount of energy lost.